of Chapter 8. The title of Chapter 8 is Series, all right? And we're going to start with something else. It's called sequences, and they're connected, but they're not the same. Let's see. Let's get some of that spring sunshine in here. All right, so we are going to do sequences to start. Remember, Chapter 8 is called Sequences and Series. I don't have handouts. But before I actually get into what a sequence is and we start investigating these things, what is going to be the point of Chapter 8, or what is the value of what we're doing here? All right, so what's the value? So I have a little animation here to help you see this. We are all familiar with the sine curve, right? We learned about the sine curve in pre-cal. And if you get on your calculator right now and you type in, let's say you're in radian mode on your calculator and you type in sine of 3, right? Your calculator is going to spit out an answer, isn't it? Sine of 3. It'll be close to what sine of pi is, wouldn't it? Pi is about 3.14. So, but what's happening inside the I don't want to say brains, but inside the computer, right? Inside the calculator, what is your calculator actually computing? Because your calculator only knows how to do 4 operations, right? Addition, subtraction, multiplication, and division. So what is it that your calculator is actually doing to return a value for sine of 3? It has no idea what sine is the way that we look at sine. We look at sine as like, well, if it's a right triangle, it's going to be the opposite side over the adjacent side, right? And we have these visual ideas, but your calculator doesn't. So what is it, right? What's going on in there? Well, here's the thing. What I'm going to do is I'm going to take a look at this sine curve, which is here in red, and I want you to take a look at this flat black line. I know it looks like it's the x-axis, but that's a flat black line. The equation of that line is x equals 0. Or sorry, y equals 0. Yes? And I put that right here. See it? Y equals 0. Now, is y equals 0 a good approximation to the sine function? Yes or no? Would you say that that those two things look like they match up pretty good to each other? Not even close, right? Not even close. How about this? How about x instead of 0? Is this x function, y equals x, close to the sine function? Like maybe in here it is, right? Like maybe around here it's pretty close, but like you go outside of that, not even close, right? Okay, so I started out with 0, then I went to x, right? So in terms of polynomials, 0 is a 0-degree polynomial. X is a first-degree polynomial. Now I'm going to try not a second-degree polynomial. Notice when I put 2, nothing happens. But when I do 3, look at this. This is a cubic function. Is this cubic function x minus x cubed over 6? Don't ask me where all this shit's coming from, okay? But just tell me if you think that's a good approximation. It's better, right? And I left this dotted one behind, didn't I? That's the one that was previous to this one? Okay, so that one wasn't that great. This one right here is better. Okay, let me try a 4th-degree polynomial. Yeah, for some reason it's not wanting me to. How about a 5th-degree polynomial? So you see this 5th degree? Is that a good approximation? It's getting better, isn't it? All right, let me try a 7th degree, 8th degree. I'm sorry, 9th degree. I'm at 13th degree already. 15th degree. Do you see what's happening here? The higher power I go, I'm fitting a polynomial function almost exactly on top of the sine function. Yes? And if I could keep going with this really, really ugly looking thing, I could actually fit it right on top of the sine function, or maybe there would be a little bit of error, but the error would be controllable by me. In other words, the further out I go, the less error I get. And this is exactly what your calculator is doing. Your calculator, when you plug in 3 into your calculator, it is replacing this x with 3, this x with 3, this x with 3, this x with 3, all of the x's with 3's, and it's computing the answer. Okay, that's what your calculator is doing. So the question becomes, where did all this come from, right? Like how did I know to put x minus x cubed over 6 plus x to the 5th over 120? Like where did that come from? Yes? It's a built-in tolerance, so there's something built into the calculator where it would go. A lot of times it depends on your setting for, I think it's called float in your settings, and that tells the calculator how many decimals you want. And so there's actually a formula that gives you the error, and so your calculator can compute the error, and as long as the difference between their answer and the error is less than the tolerance, it stops. Yeah. Nope, it's doing this. It's doing this. Yep. Okay, so the point here is this. I can approximate the sine function as closely as I want to with a polynomial, right? And this polynomial, the further I go out, the better the approximation is. The question still remains, where does this polynomial come from? Right? How do I generate this polynomial? Because if I change that right there to a plus, or if I change that 6 to a 10, this is not going to work. Every number there had to be perfect. And that's what our goal is going to be able to come up with this. And that's what the power series is all about. That's what they're called Taylor series or Maclaurin series. That's what they'll allow us to do. And the great thing, before I move on to the next example, do you remember in pre-cal that you were told that sine is an odd function and cosine is an even function? Do you notice something about this power series for sine? All the powers are what? Odd. That is what makes it an odd function. The powers for the power series are odd. That's why there's no evens in here. Okay, so if I were to graph cosine, this power series thing should look like a bunch of even powers. Make sense? Okay, so you can do this for pretty much any function. So here's another one. Here's a function 1 over 1 minus x, which is a rational function. All right, we've seen that rational function before, maybe in college algebra. It has a vertical asymptote here. I would like to approximate that. Right now I'm approximating it with 1. 1 right here. Not good. Better. 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 Well, what's happening here? It's getting closer. Like, this is really good, right? This part of it's really good. But then it seems like there's some point here where, you know what, my approximation just is not following this thing, is it? So we do have problems like that where the series that we have up here is a good approximation, but only in this little window. Okay, our window right here would be probably somewhere in here to probably infinity. It's probably good all the way out, or not infinity, to the vertical asymptote, which is at 1. So probably from somewhere around here to about 1, it's good to go with that approximation, yes? But outside of that, doesn't work. So that little window, we have a name for it. It's called the radius of convergence. And we'll be having to find out what that is. And then also, to get around it, what we can do is we can shift our power series. We'll be able to just move this whole thing over. So like if we want to approximate this region, we just shift our series over. And when you shift a series, it's called a Taylor series. When you leave a series centered at the origin, it's called a Maclaurin series. So anyway, we're going to get into this, all right? I'm just trying to convince you that there's a way to approximate functions with these power series. Here's another one, e to the x. Okay, the exponential function. There's my approximation of it. I'm using the approximation 1. That approximation sucks. 1 plus x, that's a line. That's not real good. Parabola, Not bad. Better, better, better. But watch this one. Watch this one. The further I go out, watch what happens. I don't have the problem I had in the previous one, do I? The further I go out, it's just trailing along this thing, right? It doesn't seem like I'm kind of maxing out. And so what happens is in a problem like this, our radius of convergence turns out to be everything. Okay? It converges everywhere. I just need to keep going out. And believe it or not, what I'm saying to you is this, is that e to the x is the same as 1 plus x squared over 2 plus x cubed over 3 plus x to the fourth over 24. That's what I'm saying to you, right? But it keeps going forever and ever. And that is actually the precise definition of e to the x. It is e to the x is actually this infinite power series. And it's worth talking about. All right, let me bring this back up here on a different page. If I'm telling you that e to the x is 1 plus x squared over 2 plus x cubed over 6 plus x to the fourth over 24 plus, and it kept going, right? So the dot, dot, dot means it keeps going. Then if that's true, what's the derivative of e to the x? Its derivative should be itself, right? Check this out. Take the derivative of this. What's the derivative of 1? 0. What's the derivative of x? 1. What's the derivative of x squared over 2? X. What's the derivative of x cubed over 6? So 3 comes out. 3 over 6 is 2, and you get x squared over 2, don't you? What's the next one? 4 comes out. Isn't that the same exact thing? Doesn't it appear to be reproducing the same thing? And it turns out that's exactly what happens. And it is the only function that does that. There's no other function that does that. Pardon? Yeah, and if we take the second derivative, it would work also. And what about this? What's the integral of e to the x? Itself. So what's the antiderivative of 1? X. What's the antiderivative of x? 1/2 x squared. What's the antiderivative of x squared over 2? It'll be x cubed over 60. Y'all see that? Now, we are missing something here, aren't we? What are we missing out front? The 1. But isn't an integral going to have plus a constant? And that constant's going to turn out to be 1. So what I'm getting at here, this is profound, okay? This is a huge deal. Because there's really two fathers of calculus. There's two men who created calculus. That get credit for it. There's Isaac Newton and there's Leibniz. And they both developed calculus independently from each other at the same time, and which is kind of weird. They didn't know each other, different parts of the world, and they were doing the same thing. When they got together and they started to compare their work, they realized they were tackling the same issues. They were using different notation. That's why you have Leibniz notation, dy dx, versus just y prime, right? So those different notations come from the two different people who developed it. However, even though they're both given credit as the fathers of calculus, Newton usually gets more credit than Leibniz, and it is because Newton had power series. Okay, he was using this. Leibniz didn't have this. He didn't come up with this. So what happened was you would run into a problem like this. E to the negative x squared. If right now, if I were to give you that as a problem, integrate e to the negative x squared. This is a classic integral in a Cal 2 class because you can't integrate it. There's no way to do it with your common algebraic or transcendental functions. There's just nothing. There's no technique of integration. Not happening. If we put it into Wolfram alpha, it's going to give us some weird, function we've never seen before. I showed you that a few times, right? Where it comes up with something and we're like, what is that? Okay. So there's no way to do it. So Leibniz would have just said, can't be done. Newton would say this. Newton would say, well, this is like e to the u, okay? And this formula right here, e to the u, right? Or let's go e to the x right here. Replace all your x's with u's, all right? And so Newton would have said, all right, all I'm going to do here is I'm going to rewrite e to the negative x squared using a power series. So it's going to first be 1 plus x, right? But what's x for us? Negative x squared. And then plus, it's supposed to be x squared over 2. But x for us is negative x squared. So it'll be negative x squared squared over 2. Does that make sense? I'm rewriting this formula, replacing all these u's with x squareds. Next one would be negative x squared cubed over 6. And keep going, right? And these are all just powers of x, right? Can you integrate 1? Sure. Can you integrate negative x squared? Sure. Can you integrate, what's this? This is really x to the 4th, isn't it? You could integrate that. So what Newton would be able to do is come up with an antiderivative, but the antiderivative would be a series of power functions. And then if you wanted to know like the area under a curve or something like that, he could compute it. And he could go out as far as he needs to go to be as accurate as you need him to be. Right? When it comes down to it, you can get a nice closed form theoretical answer, but you can always, approximate it too. If you're building a machine, if you're building an aircraft, there's only certain tolerances the machine can go to, right? So if I'm trying to compute something, I don't need it to be exact. I just need it to be within the tolerance of the machine. If that's good enough, then that's good enough, right? I hope that makes sense. So this is this whole thing is so much more powerful than what Leibniz was supposed to or was able to do that Newton gets a lot more props. Plus, Newton's laws of motion, and Newton was the man. All right. Have you ever heard Newton's quote? If I have seen farther than other men, it is only because I have stood on the shoulders of giants. Have you all heard that before? I love that quote. Okay, so let's take a look at a couple of more of these things just to convince you. Here's e to the negative x squared. Here's the power series. Watch me fit this power series on top of that function. See that? Fitting that thing on there real well. So I'll be able to approximate that. Shorter way of... That's right. It's actually been proven that there is no closed form antiderivative. It's been proven that. You can prove that something can't exist. Happens a lot in math. So yeah, this is it. But I mean, this is the great thing. This is the way a computer works. Okay, this is the way a computer works. It's not, your computer does not understand what e to the negative x squared is. It understands what this power series is, because this is all what? A number, subtraction. X squared is multiplication, right? Here we go. Addition, multiplication. So your computer's ready to roll with that. So this is a preferred, actually. We like this. Oh, good effect there. All right. So here's a crazy one, sine x cubed. That's a tough one. You wouldn't think that I could ever fit a polynomial on top of that because it behaves so strangely, right? Look at this thing. And yet, here I go. I don't know what my computer's going to do. I think my computer's freaking out. Hold on. Yeah, not responding. Hold on. Okay, so it's not having issues with anything except that I'm asking it to render too many images at one time, and yeah. So I think I just brought it to its knees there. Yeah, I think it's probably time. All right, you get the idea though, right? Okay. So before we can actually do this, all right, We have to completely understand what a series is. And what's a series? What are the properties of series? And before we can do a series, we have to understand what a sequence is, because series are just some form of a sequence. So we start today with trying to figure out what in the hell a sequence is. So let's begin. A sequence for us in this class is simply a list of numbers. That's the way we're going to look at it to start, okay? But in a more general wording, sequence can be a list of anything, right? List of names, a list of cars, whatever you want. But for us, a sequence is going to be a list of numbers. So since they're a list of numbers, I can call the first number a sub 1, the next one a sub 2, the next one a sub 3. And maybe I keep doing this, and at some point I stop and I put a sub n. That would be a list of n numbers, right? We're using subscripts because if we use subscripts, we'll never run out of them, right? You could have a list of 2,000 numbers, A1, A2, A3, all the way to A2000, A sub 2000. This is what we would call a finite sequence because it stops. That says finite seq. But it is okay to also have an infinite sequence. So you can have A1, A2, A3, and when we want to tell you that it never stops, we just put dot, 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 and that dot, dot, dot means it goes forever. So this would be an infinite sequence. We will let n go to infinity, but you can't really let a number equal infinity ever. You know what I'm saying? Like infinity is the idea of letting n go to that, but you can't like just say replace n with infinity. All right, so we have finite sequences, infinite sequences. An example of a finite sequence, the even numbers between 0 and 10, including 0 and 10. So that'd be 0, 2, 4, 6, 8, 10, right? Finite sequence. Infinite sequence, all even numbers, right? Okay, now with this idea, recall the concept of a function. When we had a function back in college algebra, we had like input goes through a function, which we usually call f. That was the notation we like to use, right? Then we had output here. You plug something in to this function, it's going to do something to that number. It's going to spit a new number out, right? So usually it was numbers in, numbers out. So I'm going to put here R, double struck R, meaning that I plugged in real numbers came out. X squared, right? You plug in 2, it spits out 4. You plug in a real number, spits out a real number. Okay, that's the classic idea of a function. Our example being f of x is x squared. And what we did is if we tried to evaluate this, we did something like f of 1 squared is 1, f of 2 squared is 4. Could I do f of pi? Yes? That'd be pi squared, wouldn't it? I could do any number I want, right? I can plug any number I want into that. I could do f of negative 1.75. That would be okay also, right? In other words, for this particular function, there wasn't really a restriction on the domain. The domain was everything. And so when we graphed it, to represent all of the matching ordered pairs, we knew that we plug in 1, we get 1. We plug in 2, we get 4. We plug in 3, we get, pi squared way up here. And if we can imagine connecting them all together created the graph, didn't it? And it went in both directions like this. That's what our function looked like. What we're gonna realize now is that a sequence, we're not going to think of it necessarily as a list of numbers as much as we want to be able to look at a sequence as a function. All right? So here's some kind of a new concept. What if I define, or sorry, I'll say it this way. What if I restrict the domain to positive integers only? And take that same function. What are you allowed to plug in now? Positive integers. What are the integers? 1, 2, 3, 4, 5 forever. 0, right, is an integer. -1, -2, -3, -4, -5 forever. Those are integers. But I said positive integers, right? So that would just be 1, 2, 3, 4, 5, 6 forever. All right? So you could plug in 1, you could plug in 2, but you couldn't plug in pi, and you couldn't plug in -1.75. How do you mean? Well, it'll always be positive. Okay, yeah. For x squared, it wouldn't matter, but yeah. So let me ask you what the graph of this would look like, though. Half parabola, would it be the whole parabola, though? You're not allowed to plug in anything but integers. So at 1, I would have what? 1 dot, right? At 2, I would have a dot up here, right? And at 3, I'd have a dot up here. And then at 4, I'd have one up at 16. But there would be nothing in between, would there? There'd be nothing in between. Do y'all see that? So if you restrict your domain to just positive integers, then you do not have a nice continuous function. You have a bunch of dots instead. You follow? Okay, so we will want to restrict the domain to positive integers. We're trying to get ourselves to a sequence here. I need a way of letting you know I want to restrict to positive integers without having to write down, hey, let's restrict the domain to positive integers. So if we write f of n equals n squared, it is understood that n must be a positive integer. That is, n must be an element of double struct z with a plus on the top right. Okay, you've seen double struct R is all real numbers. Double struct Z are the integers. The plus sign in the top right means positive integers. So what we're doing is we're switching our variable out, right? Instead of using x was always a variable we used in college algebra and in calculus. X always represented a real number, any real number. If we replace the x with n, then everyone understands that that n needs to be a positive integer, all right? Now, there are going to be times also where we allow n to be 0, all right? But we usually never let it be negative. But to start out, First day, let's just assume n is a positive integer. Okay, now, if this is the case, right, if we've got this here, then I can write f of 1 equals 1 squared, right, which is 1. I could write f of 2 equals 2 squared, which is 4. F of 3 equals 3 squared, which is 9. And I could keep doing this all day long, couldn't I? And what I'm creating here is a list of numbers, right? The first number, right? When I say first, notice it comes from when I plug in 1. When I plug in 1, the first number I get is 1, right? When I plug in 2, that's like the second number. The second number I get is 4. When I plug in 3, that's like the third number. The third number I get is 9. Do you see that? The sequence here is 1, 4, 9. And this is the last little change in notation we're going to make. Because I don't want to write f because you might think it's a function, you might want to graph the whole parabola, I'm going to change one more piece of notation on top of using n to really stress to you that this is a sequence. I'm going to change it to this. Instead of writing this up here, whoa, give myself a little more room. Instead of writing this, I'm going to write a sub n equals n squared. And let's see if that makes sense. All we're doing is it's just an adjustment in notation. The n squared equals n squared is the same, right? The only thing is instead of writing f of n, I'm writing a sub n. And so if I ask you now, what's a sub 1, you replace the n right here with 1, right? Which means you replace this n with 1, so you get 1 squared, which is 1. A sub 2 is 2 squared is 4. A sub 3 is 3 squared, which is 9. Okay? And so I hope that by writing it a sub 1, a sub 2, a sub 3, that you can see that a sequence, right? This sequence of numbers is a function. What it does is it takes a number in, like it takes this number 1 in, does something to it and spits out a number. Then it takes 2 in, spits something out, then 3, and then 4, and then 5. Make sense? You could call instead of f, you could call it a, but we're using subscripting instead of the parentheses with an x in there. And it's just points. It's just points. Yep. Okay. Now this idea of restricting a function to a domain where you're just getting points out is actually a pretty big deal. Anyone here going to do more like statistics or has done statistics? Okay, there are two major fields in statistics. You study what are called continuous variables and discrete variables. Continuous variables are variables that can take on any values. So like if I take a can of soda, right? Take a can of soda and I say how many ounces are in it. If you had a very precise instrument to measure it, it's not going to be 12 ounces dead on, right? It might be 12.0356 ounces or something. That can take on certain values, and they can be everything in between, right? They can be 0 to, let's say, I don't know what the max would be, but it could be anything in between, right? You get a can that has 11.75 ounces in it. Now, compare that to something like the number of students in this class on a given day. That's a discrete variable, right? We count the people in here, right? That's it. It can only take on 0, 1, 2, 3, 4, 5, all the way up. They're all integers. That's discrete variables. So when in statistics, you have two branches that you study. One is discrete, one is continuous. What we're actually kind of doing is getting into the discrete cases here. We are talking discrete math now, if that makes any sense. Okay, now, if we look at this, we're almost done here. I want to write this list of numbers out in a way that you can see the sequence. So below this, I'm going to write out a set of braces, 1, 4, 9, 16, ... This right here is another way we represent that sequence. That is a sequence of numbers. Now, can you look at that sequence and see the pattern? Can you tell that that's n squared? Yeah? Okay. That's right. So by looking at that, you have to be able to recognize that that is n squared. Now, what if I had given you this instead? Is that enough for you to have said n squared? No, because you could argue with me that the next one should be 7, and they're just going up by 3 every time, right? So you have to have enough information in a given sequence for you to be able to conclude that it comes from like n squared here. You have to have enough of them to be able to say, okay. There's no rule, there's nothing. No, it's just, I'm sure a clever mathematician could come up with a sequence that the next one would not be 25. Okay, but like for us, what we're doing, we're not trying to trick you. You know, it's just like, do we see the pattern? Yes. Okay. I'm sure there's a sequence out there that I could come up with where it would do something different. Okay. So everyone kind of okay on just the basic ideas here? So notation, we've got notation down. One more thing with notation. I said Z plus, right? That's also equivalent to double struck N. What, the sun's coming out today? Double struck N is the natural numbers. The natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That, not 0. The natural numbers do not include 0. In the evolution of the human mind, 0 came after we had figured all the other numbers out. 0 was a big deal. The concept of nothing came later. If you believe in that sort of evolution, then, you know, think about it. Think about the concept of like, this is mine, you know, like get away from my food, you know, like I have 2 apples, you know what I'm saying? The concept of nothing is a more advanced idea. It's a deeper thought, so it came afterward. So it's not part of the natural number. Then you stole your apples, and then you just, yeah, I don't know what you do. So, yeah. So, all right. Now, a little bit of both. Okay, so what about this? I'm going to write down a sequence, and there's different ways to write a sequence down, and so you've got to see the different notations. Let's say that I want to write the sequence. I want you to be able to understand that I want the sequence for n squared again, but I want you to start at 3 and never stop. How many different ways could I do that? Well, I want you to start at 3 and never stop. We're talking about n squared. Let me write it down. I want to do n squared, start at n equals 3, and don't stop. In other words, it needs to be an infinite sequence. So how could I write that? How could I represent that? One way I could do is just write it out, right? So what would it be? 9, 16, 25, 36, until you're happy that people understand what you're doing. Oh yeah, the dot, 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 in math, 3 dots is what you need to say it goes forever. But if you put 5, I'm not going to get upset. I always just do dot, dot, dot. I don't even count like how many I do. I just dot, dot, dot. Okay? But 3 is the standard. So I think that would be enough, yes? All right, here's another way you could do it. That's another notation. It's almost like an index on an integral or like on a sigma. You know how the sigma notation, you had an index where it started on the bottom and ended on the top? This is kind of like that, but it's a set of braces around your actual function, n squared. And then on the bottom right is your starting, and then the top right is your ending. So, sorry? Yeah, we could use k. If you wrote k for this, it would be the same thing, yeah? The n is a dummy variable. It actually comes from the fact that n is a natural number, so we use n. But it would not be wrong to do this, but everything's got to go to k. Okay, that's another way, right? Here's another way to write it. You could write a sub n equals n squared, n greater than or equal to 3. Okay, I'm giving you different ways of doing this, okay? Also, I'll count this one too as a third option. There's 4 different ways to write that series, the sequence. So I define my actual sequence here. I tell you where to start it, right? N is greater than or equal to 3. All right, so let's do an example now. List first 5 terms of this. Terms. We're going to call them terms. They're not separated by addition or subtraction, but well, that's a good question. How do you write the answer? Do you write just number, comma, or do we put it in the braces? The answer is you put it in the braces. That's a brace, yes. Okay, so we're going to start with n being 2, and then we're going to go and we're going to do this, and we're going to list 5 of them out. So the first one would be 1 over 2, then 1/3, then 1/4, then 1/5, fifth, and then 1/6, right? And then dot, dot, dot. It would keep going, right? But that's the first 6. Yes, we're just going to, the next test is just going to be about 20 of those. That'll be good? This obviously has to get more complicated, right? All right. So here's where it starts to get a little more complicated. Let's look at some common sequences. We are going to need to be able to recognize sequences that'll come up kind of often, and we're going to need to be able to look at the sequence of numbers and from it recover the function. So like, you know, when we saw 1 and then 4 and then 9 and then 16 and 25, we knew that came from n squared. We need to be able to do that for a lot of different things. So let's try, let me give you a sequence and let's see if you can recover the formula, all right? So find the a sub n for this sequence. We'll start easy. Just n. Just n. right? A sub n equals n. That's right. So the answer would be this. A sub n is n. Yeah, maybe. All right, so if you want to list out just numbers in order, you just use n, right? All right, how about this? I'm just gonna keep listing these out, and to the side we'll put them. How about this? Close. N minus 4. N minus 4. So what it is it's this same sequence, isn't it? But everything has been shifted to the left by 4. Instead of 1, you want negative 3, so you subtract 4 from it. Instead of 2, you want negative 2, so you subtract 4. So these are jumping up by the same amount, plus 1, plus 1, plus 1 each time, just like this was, but the whole thing's been moved. Does that make sense? So we have a sub n equals n minus 4. That's right. Yeah, because we're saying n has to be a natural number, we couldn't just have started it at negative 3. I mean, in the big picture, you can, just not here, not now. I mean, there would be nothing wrong if you did that. Okay. How about this? N times 2 or 2n. Those are just going to give you your even numbers, right? Okay, I'll put a star next to this one. You need to know how to get the even numbers very easily, all right? 2n. I mean, all of these should be starred, but that one comes up often enough. Okay, let's see about this. So those are evens again, right? We're shifting them by how much? 8. Every one of these, right? I take 8 away from this, I get this. Take 8 away from that, I get this. Take 8 away from that, I get this. Take 8 away from that, I get, right? So 2n minus 8. Still good? All right. Two n plus 1. Those are the odds, right? Starting at 3. The odds are always 1 more than the evens. So we use the same formula that we use for the evens. In this case, we just add 1 because we want to start with the evens, which is what? 2. And then we want to get to 3, so just add 1. Then you plug in 2. 2 times 2 is 4, plus 1 is 5. Make sense? How about if I want, oh, go ahead. Yeah, so that was what I was going to ask. What if I want to start at 1? 2n minus 1. There you go. Y'all catching on to this? So those are your odds. Here are the evens starting at 0. Here are the odds starting at 1. But you could start the odds anywhere. You could start the evens anywhere. Okay, how about this? Oh, yes. Trying to get 1. Yes, you could start, but remember we said we wanted n to start with 1. So if we're going to start, yeah, if I started today and say let n be anything, then we could have all sorts of different formulas over here, right? So we wanted to start with like a base point. Hold on just a second if y'all don't mind. I hate to do this in the middle of class, but we're here in class, we're having fun, we're doing sequences. No. No, what I'm doing is I am VPNing into my house, and I am turning on the pump to my pool, and then I am now changing one of my valves over to the heater. And if the sun's out, I've got a solar thing on the roof of my shed that I can pump the water through the solar panel, and it'll warm up the pool. So, and then I'm gonna look, because I have a camera. I have a camera that shows me two thermometers. One of them is the pool water coming into the heater, and the other one's going out. So I can look at the temperature differential. Yeah. And I need some sun. I need a couple of days of solid sun, because, I mean, it works great, but you got to have like 3 good days of sun for it to really be effective. You're talking about 20,000 gallons of water. It's hard to change it by 5 degrees. You know, it's a lot of calories, huh? Yes. And then I have a different one for cooling it, but that's a whole different principle. I built it all. Yeah. I have a board. I'll show you if you're ever interested. I'll show you. I've got a picture of the board I put in my shed. It's like a control relay, 16 relays that control like high inductive load relays, and I run all my power. I think I have 5 valves, so like we have a slide, so I can turn and the water will start coming down the slide, and then I can turn it and the heater will. This is fun. It's fun for me. Fun stuff for me. Anyways, let me just make sure that that it is going. Yeah. The toughest part was the VPN thing, though. Getting into there to be. Oh shit! I just turned the pump off. Getting in there to control these from here. I know that doesn't sound like a big deal, but the board, the 16 relay board that I had, has a static IP address, so I couldn't port forward to it, and so I had to VPN in and act like I'm actually there. I don't know. I don't know how technology, background you have, so I could just be like, it could all be not make any sense, so I'm not trying to talk over you or anything. Okay. Back to this. I should have given you an example while I was doing that. -2/5, 0, 2/9, 4/11, ... I'll give you a second. No one say the answer, okay? If you get it, no one say it. I don't think it's sunny enough. Anybody get it? Don't say it. Anyone get it? No? Okay, so let me give you a hint, all right? Look at every single one of these as fractions and, focus on the numerator and denominator separately. And tell me if you can see a pattern in the numerator and denominators. What's the top? The numerators are what? Evens, starting with what? -2. And the denominators are odds starting with 5. You see it? Look, let me rewrite it. -2 over 5. The next even was 0 over, the next odd was what? 7. It didn't matter, though. You see? Then 2 over 9, and then 4 over 11. You see it now? So my sequence, a sub n, I need to create my numerator, which is even numbers starting with -2. How do I do that? 2n minus 4. 2n minus 4. 2n gives you the even starting with 2. 2n minus 4 gives you the even starting with -2. The bottom needs to create the odds starting where? At 5. So 2n plus, it's got to be an odd. If you add 4, you're going to be an even, right? So 2n plus 1 starts you at 3, doesn't it? Look back in your notes. 2n, what, did I say 2n plus 1? Yeah, it starts you at 3. So 2n plus 3 would start you at 5. And then keep adding 2, 5, 7, 9, 11. Does that make sense? Okay. Just curious here. This sequence of numbers heads somewhere, right? These numbers keep changing. I wonder what they head towards. I wonder if they head to a number, if they just get bigger and bigger. Like over here, these numbers 3, 5, 7, 9, they just got bigger and bigger and bigger. These got bigger and bigger and bigger. These got bigger and bigger and bigger. This one goes to 1. Why? You're asking what happens as n goes to infinity here, right? Infinity over infinity? L'Hopital's rule? Right? 2 over 2 is 1. So actually, these fractions, they get closer and closer and closer to 1 as you go out. All right, just kind of get you thinking about that. But let's try another one. That would be a convergent sequence, yes. Yep, and we will do that probably next class. Okay, how about this one? -1, 1, -1, 1, -1, 1. -1 to the n? -1 to the n. Would that work? First, start out by plugging in a 1. What would you get? What's -1 to the 1? -1, right? Now you plug in 2. What's -1 squared? 1. Then -1 cubed? -1. -1. This is a big time formula right here. This is what we call an alternating sequence. All right? This is an alternating sequence. It starts with a negative, doesn't it? Starts with a negative. I'll take you back to this right here. Bless you. Remember the sine one I did here? Remember the sine one I did? Remember this in the beginning? Notice the signs. Positive, negative, positive, negative, positive, negative. That's an alternating series. The formula that creates this alternating series must include in it that -1 to a power to create the alternating, to make that alternating happen, right? So we're just kind of seeing how we're going to make things alternate later. Now, what if I want to make an alternating series that starts at -1, not at +1? I mean, sorry, at +1 instead of -1. I don't add 1. Don't add 1. You have to do something else. Multiply by -1. So you're saying take the series that I had just before and multiply by -1? And then it would change the signs of everything, wouldn't it? I agree. Can I just write it down over here, what you're saying? You want to take this and multiply by -1? So that power on the -1 here is 1. Same base, add the exponents, -1 to the n plus 1, which is what I heard you saying. So use this instead. A sub n equals -1 to the n plus 1. See, because what happens now is if I plug in 1, 1 plus 1 is 2. So my first one's going to be -1 squared. That's positive. Then when I plug in 2 to get my second piece, 2 plus 1 is 3. Now -1 to the third is a negative, so now I'm negative. Does that make sense? Could I have used n minus 1? Yes. Could I have used n plus 3? Yes. So there's actually a bunch that you could have used. Same with this one. I could have used n, or I could have used n plus 2, or I could have used n plus 4, or n minus 2. There's a bunch that you could have used. As long as you're going to get even, then odd, even, or sorry, no, in this case, odd, then even, odd, then even. Yes. What's not 0? N. If it's n minus 1, if you plug 1 in, you get an exponent of 0, which is okay to have. Yep. We all right? Alternating. This is also an alternating sequence. What's that? So big time one. So a lot of times you're going to want to create an alternating sequence, and we'll say, hey, we want it to alternate. We want to start with negative. We'll use this. We want to start with positive. We'll use this. All right, next one. What about this? That's too much right now. Sorry. That's still too much. Okay, hold on. There we go. It's alternating, right? So look at the numerators. The numerators, -1, 1, -1, assume the next one's 1. So the numerator should be -n to the what? Just n, right? Over, that's right. 5, not 5n, 5 to the n. 5 raised to the n. 5 raised to the n. Because the first one is 5, the next one, 25, is 5 squared, the next one is 125, which is 5 cubed, right? 5n would have been 5, 10, 15, right? Y'all see that power? Now, do you see why I changed my mind? Look, if I had done, I was going to do -3, 3, -3, but if I would have done 5, 25, and then 125, oh no, I guess that would have been okay. Yeah, that would have worked. Who cares? All right. I think that's sufficient for now. You would just put a 3, yeah. And you would put it outside. You would not put it inside with the -1. It would be outside by itself, and it would be a constant. It would just be sitting there the whole time. Absolutely. Could you do this? Would this be okay? Could you do that? Yes. Because the -1's to the n and the 5 is to the n. So you could do that. So there are multiple what's the word I'm looking for? When it comes to formulas, you can have formulas that are different, that create the same sequence. All right, someone could have used n plus 2 up here instead. All right, and then it would look different, but still create, so it's not unique. There you go, that's what I was looking for. These formulas are not necessarily unique. As long as they generate the same sequence of numbers, it's good to go. All right, let's talk about factorials. So there's a certain arithmetic operation that occurs often enough in mathematics that we have a special name for it, and it is, you know, if I ever want to take 5 times 4 times 3 times 2 times 1, right? If I ever need to do that, or if I ever need to do, like, I don't know, just 3 times 2 times 1, or 10 times 9 times 8 times 7. I don't want to have to write that all out, right? I want to be able for you to understand, look, I want you to do that. Start at 10 and multiply by the next number lower. Keep going until you get down to 1. So instead of writing all this, what we do is we use this notation called factorial. I would write 5 with an exclamation point. Here, 3 with an exclamation point. This one, 10 with an exclamation point. The exclamation point is telling you that that really means 10 times 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. Okay? That's called a factorial. Now it's used in things like statistics, combinations of things. Let me take something very simple. If I have 3 horses in a race, how many different ways can they finish, first, second, and third? How many different ways? So let's say I have horse A, horse B, horse C. All right, how many different ways can they finish? A first, B second, C third, or you could have A. So let's list them out. You could have A first, then B, then C. You could have A first, then C, then B. You could have B first, then A, then C. B first, then C, then A. You could have C first, then A, then B. You could have C first, then B, then A. Right? Did I cover them all? How many are there? 6. Okay? Now let's think of it a completely different way. There are 3 places they can finish. First, second, and third. How many different ways can I finish first? There's 3 horses, right? So there's 3 different ways. That can be an A, a B, or a C, right? So there's 3 ways that can happen. Once that's determined, second place can only be one of the 2 left over, right? 2. And once that one's determined, the third place can only come from 1 horse. 3 times 2 times 1 is what? 3 times 2 times 1 is 6. Okay? The answer to this is 3 factorial. So now if you have 10 horses in a race, how many different ways can they finish? 10 factorial. Okay, so it's used a lot in things like combinations and permutations and blah, blah, blah. So big time in statistics, but it's also used here a lot. All right? Now, there is one thing I want to say about, a couple other things I want to say about factorial. 1 factorial is 1, and that makes perfect sense, that 1 factorial would just be 1. But 0 factorial, you would think would be 0, but it's actually 1. And this is by definition. we define it that way. There's this YouTube channel or something. It's called like Math File, or what is it called? Math File. Phile, Math File, or something like that. And it's this guy, and he tries to explain why 0 factorial is 1. So if you want, you can go watch it. It's okay. But as far as like what we are concerned with in this class, factorials only make sense on integers. Like pi factorial, what is that? Okay, I mean that factorials for us only on integers, but there is a way that you can do pi factorial, but it's beyond the scope of this class, all right? So everyone just remember, 0 factorial is 1, all right, by definition. Anything to, yes, well, other than 0 itself, right? Yes. So now, some other properties of factorial. I've told you what it is by writing out examples, but by, what if I'm trying to explain to someone what is n factorial, I'm telling them first you start with what? Like, so what's 5 factorial? First you start with 5, then you multiply by 4, and then 3. So n factorial, you start with n, then you go what? N minus 1, and then you go n minus 2, and I keep doing this until I get down to what? 1. Just 1, right? Just keep doing that as long as it makes sense until you get to 1. Does that make sense? This is really the precise definition of what n factorial means. This is well defined as long as n is greater than or equal to 1. And if n is 0, we know the answer is 1 by definition. Okay? Do you see why the 0 case is kind of tricky? Because if I plug 0 in right here, what's 0 times all this? 0, it shouldn't be 1 then, right? That's why we have to define it that way. Okay, so watch this. What is n plus 1 factorial divided by n minus 1 factorial? What is that? Well, by the definition, right, this is n plus 1 is where I start, right? Because notice the parentheses around the n plus 1 tells you that's the number in front of the factorial. So I start with that, and then the next one, I subtract 1 from that, right? What if I subtract 1? I'm going to have n, and then what's the next one? N minus 1, and then n minus 2, then n minus 3, and I keep doing this until I get to where? 1. Yes? All over. Now what's the bottom? Start with n minus 1. Then the next one's n minus 2. Then n minus 3. And I keep doing this until I get to 1. Yeah? Do you see anything? Get some cancellation here, don't I? N minus 1 canceled with n minus 1. N minus 2, n minus 2. N minus 3, n minus 3. You see that? So I wonder if there was a more efficient way to do it. And the answer is yes. Let me show you. What is this right here? Starting right here, n minus 1 times n minus 2 times n minus 3, go down till you get to 1. What is that? That's n minus 1 factorial, isn't it? So watch this. I'm going to start this problem over. N plus 1 factorial over n minus 1 factorial. What I'm doing here is I'm looking at this and I'm saying, look, n plus 1 factorial should be bigger than n minus 1 factorial, shouldn't it? So what I'm going to do is I'm going to start writing out n plus 1 factorial until I get to n minus 1. Watch. I know it's n plus 1. The next one we said was n, right? Then, watch, I'll do it in different color. N minus 1 factorial is where I will stop. So what's in black is actually representing, instead of keep on writing all these, I'm saying just stop here and just write all those as n minus 1 factorial, and that means it keeps going starting at n minus 1. And I'm just going to write that on top of what? N minus 1 factorial. I'm not going to touch the bottom, and then what's going to happen? They're just going to cancel. Yeah, I mean, well, yeah. Yeah, I mean, it can get a little bit messy, but it's not too bad. Yeah. Make sense? Okay, how about this one? How about 2n minus 1 factorial over 2n plus 3 factorial? So which one is bigger, 2n minus 1 factorial or 2n plus 3 factorial? 2n plus 3? You would think, right? Yes? Okay, so let's try this out. I'm going to start writing the bottom one out. The first term would be 2n plus 3, right? The first factor. Then what? Subtract 1 from that. 2n plus 2. Next one, 2n plus 1. Next one, 2n. Next one, 2n minus 1. And then I'm not going to keep going, right? Because it's matching what's up here. So I put factorial on the end of this. Please understand, the factorial is only attached to that one. This, what we're saying is from here on, 2n minus 1 factorial keeps going. This stuff all kind of got peeled off the front. It's like you peeled it off the front and put it to the side. Now on top of this is 2n minus 1 factorial. And we get cancellation. What's still up top? A 1. So your answer is 1 over 2n plus 3 times 2n plus 2 times 2n plus 1 times 2n. Just leave it like that. Yes? Yeah. How many times I had to do it? It was like the difference between these two, right? This one was 2n plus 3. This one's 2n minus 1. There's like 4 between there. That's how many wound up getting peeled off. I'm not sure I would say it a certain way. I mean, all I would say in a problem like this is just simplify this. And to simplify it with no factorials, right? Because our final expression has no factorials in it. I'm not sure. I'm still not sure I follow. I'm sorry. Okay. All right. Think it through and then come back to me with it. Okay. One last. I give you a series, a sequence, and you give me the formula. I was off on that. 343, sorry. Do you want help or you want to do it? Give you a second. While you're doing that, I'll write your homework down. We still have a lot to do in this section. We have not finished 8.1, okay? Just got our feet wet. There's the homework for it. Anybody think they have it? You could. Yeah. Do you want a hint? No hint? Okay. Yeah? Is there a marker over there? Is there a marker? You can go put it on the board. Can you turn on the light? I can't see that. Can you turn on the light over there? I'll have the class look at it. Y'all can look over there and tell me if you think it's good or not. What do y'all think? A sub n? Okay, let's, because time's almost up. It's an alternating sequence. So first thing you throw in there is a -1 to the n. That should get you started off on negative, then positive. So the -1 to the n, I think, is good. Let's do the bottom. 749, 343. 7 to the first power, 7 squared, 7 cubed. 7 to the n, I agree. Now look at the top, 2, 6, 24. And they're saying it's n plus 1 factorial. What are the factorials? What's 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5? Let's list them out. 1 factorial is 1. 2 times 1 is 2. 3 times 2 times 1 is 6. 4 times 3 times 2 times 1 is 24. Well, but we started off with 2. So we needed to take it, n factorial, and shift it over by 1, which is n plus 1 factorial. That's correct. So if I plug in n to that factorial, if I plug in 1, 1 plus 1 is 2. So you start with 2 factorial, which gives you 2. And then you plug in 2. 2 plus 1 factorial is 3 factorial. That gives you 6. And then this one. So that is correct. So the answer was -1 to the n. And you could write a sub n equals, or that. That's fine also. N plus 1 factorial over 7 to the n. Extra credit. I'll keep a strong mental note of that. Okay, everyone. I put the homework up here. It's only a few problems. Go over your test. You know, review. Go back through and see if you can find your mistakes. Just on your own, for your own good, not necessarily for any extra credit or anything.